Hello everyone. Today we are going to discuss field due to uniformly charged insulating sphere by using the Gauss law. This is an application of Gauss law. So let us consider a insulating sphere. Okay. So this is insulating sphere. Insulating sphere, and let capital R be the radius. Okay. This is radius of the sphere or insulating sphere, and let the sphere contain plus Q charge. Okay. Let the sphere contain plus Q charge. This is charge on the insulating sphere distributed uniformly, okay, throughout the volume. Clear? So as I said earlier, we want to find field, that is electric field due to uniformly charged insulating sphere by using Gauss law. Now, for uniform distribution of charge, we use the concept of volume charge density, and it is denoted by symbol rho. Volume charge density is charge per unit volume, okay, and it is constant, okay. So volume charge density is constant at each point on this insulating sphere because the charge distribution is uniform. So we need to note this, okay. So we can write rho equals charge on insulating sphere divided by volume of insulating sphere. So I'm writing in magnitude, okay. Charge on insulating sphere is Q in magnitude divided by volume of insulating sphere is 4/3 pi and R power 3, okay. So we have this. Now we consider two cases, okay. One, we are going to find electric field inside, okay, the insulating sphere, and next we are going to find electric field outside the insulating sphere. So let us discuss, okay, this. So we want to find field inside the insulating sphere, okay. Now I'm redrawing this sphere over here. It is the same sphere, okay. It is the same sphere. Now this is radius, okay. So the volume, okay, sphere is 4/3 pi R power 3, okay. Now what we do, and charge, so let me write it at first this also. and charge is Q in magnitude. So we have this. Now we are going to apply Gauss law. Okay, so in order to apply Gauss law, we must have closed surface or Gaussian surface. So we need to select or choose Gaussian surface, okay, inside this sphere. So let us draw a spherical Gaussian surface. Okay, let us draw a spherical Gaussian surface which is concentric with the insulating sphere. Okay, so this is spherical Gaussian surface having radius r, okay, and is concentric with the insulating sphere. So we have this. Now, as I said earlier, charges are distributed uniformly throughout the volume of the insulating sphere, so that the insulating sphere encloses charge or charges, and we have this. Okay, clear? And let the charge enclosed by Gaussian surface be Q E N C. Okay, this is charge inside or enclosed by the Gaussian surface. And what we find is that the charge inside the Gaussian surface is less than the total charge on the insulating sphere. Clear? So we need to note this. And the volume of Gaussian surface, okay, its volume, okay, the volume of Gaussian surface equals 4/3 pi, and we have small r as the radius, so r power, that is small r power 3. So this is volume. Now charge density, okay, we know, as I said earlier, it is constant throughout the volume of the sphere. So for Gaussian surface, we write rho equals charge inside the Gaussian surface. Okay, so we use this concept, okay, charge by volume. So charge inside Gaussian surface is Q ENC divided by volume. So volume of the Gaussian surface is 4/3 pi and small r power 3. So we have this. Clear? Now so we are going to equate these two. Okay, so on equating, what we get, so let's call it equation 1 and this as equation 2. Okay, now we can write from 1 and 2, okay, Q by 4/3 pi capital R power 3 equals Q enclosed, okay, by 4 by 3 pi, and we have small r power 3. So what we get, okay? So this cancels out. So we can write charge inside the Gaussian surface equals, so on simplification, we get this, okay? So we have this. And let us call it equation 3. So this is equation 3. So I'm writing, let me write over here, okay? Charge inside Gaussian surface equals charge on insulating sphere, okay? And we have small r power 3 divided by capital R power 3. So we have this, and this is equation 3, okay? So this is the relation between charge inside the Gaussian surface with the total charge, okay? And we find radius of Gaussian surface by, so we can write in this way, okay? Radius of Gaussian surface by radius of the sphere whole power 3. So we have this, okay? So we have this. Now, I'm erasing this, okay? From Gauss law, we can write total electric flux equals surface integral of electric field throughout the closed surface or Gaussian surface equals 1 by epsilon naught times the charge inside the Gaussian surface. So we can write QENC divided by epsilon naught or epsilon 0. Clear? Now, we take this, okay? And simplify to get electric field. So in order to calculate electric field, okay, from this equation, we use the symmetric condition, okay, or we use the condition of symmetry. So what is the condition of symmetry? Okay, let's understand in brief about the symmetrical charge distribution and its condition, okay? So by symmetry, okay, or for symmetry, we must have this, okay? We must have this electric field on the surface, that is electric field on the Gaussian surface must be constant, okay? So this must be constant on the Gaussian surface. Next, this dot product, okay, can be replaced by algebraic product, okay, that is EDA, and this is possible only when electric field is parallel to the area vector. So there are other conditions for symmetry also. So I'm taking these two conditions. If you want to know more about the condition of symmetry for uniform charge distribution, you can visit my lecture video. So I'm going to add the link on the description. Okay. Now, I'm taking or redrawing okay the shaded region. Okay, this is the shaded region, and the radius okay is small r, and it is enclosing charge okay q enc, and the charges are positive. Okay, so keep in mind. So I'm drawing charge. Okay, so we have this. So this is what? This is a Gaussian surface. This is a Gaussian surface. It is enclosing charge QENC. And we know electric field due to positive charge is directed radially outward. So it is directed radially outward. Okay, is directed radially outward. Now, what we do is that we take small elementary area on the outer surface, okay, on the outer region of the Gaussian surface. So this is a small elementary area having magnitude, let's say dA. Okay, so let us take a small elementary area on the outer region of Gaussian surface. Okay, so let us take a small elementary area. So we have this. Clear? Now we find vector area, okay, on this equation, and we know area vector can be expressed in this form. Okay, unit normal, this is unit normal times the magnitude of the area, and unit normal gives the direction of vector area. So let us draw a unit normal, okay, n cap, which gives the direction of vector area. So this is unit normal, and it gives the direction of vector area. Okay, unit normal which gives the direction of vector area. So this is okay. So we have unit normal which gives the direction of vector area. So what we find is that area vector and electric field are parallel to each other. Okay, they are parallel to each other. So this condition for symmetric charge distribution is satisfied, and electric field at each point on this Gaussian surface is constant. So this condition is also satisfied. Okay, so we use these two conditions, okay, in order to determine or find electric field from the Gauss law. And if these two conditions are satisfied, then we can take electric field out of the integral and calculate or determine it. Clear? So we need to note this. Okay, so I'm erasing this. Now we can write Clear? And this is 1, and we can take E out of the integral. Okay, it is constant in magnitude at each point on the Gaussian surface and is acting in radially outward direction. Okay, so we have this. Now this gives the total area of Gaussian surface, because dA is the area or elementary area on the Gaussian surface. So we can write in this way. Okay, and this gives this integration. Okay, is 4 pi small r power 2. Okay, so we have this 4 pi small r power 2. So finally we can write electric field E equals, so on arranging, so I'm writing in this way. Okay, 4 pi epsilon naught or epsilon 0, and we have Q ENC divided by small r power 2. So let's call it equation 4. Okay, because we had derived this expression, which is equation 3. Clear? Now so I'm erasing this. Okay, now from 3 and 4, okay, we are going to put charge inside Gaussian surface. Okay, from this expression, that is from equation 3 in equation 4. Okay, so we get this E equals 1 by 4 pi epsilon naught, and we have QENC, that is Q small r power 3 by capital R power 3, and we have 1 by R square. Okay, so we have this. Clear? So let us simplify it further. So we get this electric field E equals 1 by 4 pi epsilon 0 Q, and we have small r divided by capital R power 3. So this is the expression for electric field. Okay, inside uniformly charged insulating sphere. So this is field. Okay, this is field inside uniformly charged insulating sphere. So we have this, and what we note from this expression is that for radius of Gaussian surface less than the radius of insulating sphere. Here we can write in this way: small r less than capital R. Okay, for this electric field is proportional to the radius of the Gaussian surface. So we have this. So this is to be noted. Okay, now for small r equals 0. That is at center. So from this expression, okay, so let's call it equation 5. From equation 5, electric field equals 0. So we get this. Clear? So I'm writing equation 5 over here, okay? So E equals 1 by 4 pi epsilon naught Q R divided by capital R power 3, okay? This is equation 5. And this is for the condition small r less than capital R. So we have this. Clear? Field outside the sphere, okay? So we have this now. So we have to choose a Gaussian surface outside the insulating sphere. So I'm writing in this way, okay? Small r greater than capital R. So I'm drawing the same sphere, okay? It is the same sphere, same insulating sphere, okay? So as I said earlier, charge plus Q is distributed uniformly, okay? And its radius is capital R. Okay. Now, we apply Gauss law, okay? Gauss law to find field outside the uniformly charged insulating sphere. So for this reason, let us draw a spherical Gaussian surface, okay, which is concentric with the insulating sphere. So this is spherical Gaussian surface of radius r and concentric with insulating, sorry, its radius is capital R, okay? Sorry, small r, its radius is small r, and concentric with insulating sphere. So we have this. Okay, so we have this. Now, this Gaussian surface, it is enclosing charge Q. So we have this, okay? It is enclosing charge Q, and the volume of the Gaussian surface is 4/3 pi, and the radius is small r, okay? Small r power 3. Clear? Now what we find, electric field is directed radially outward, okay? So let's say electric field is directed radially outward. Radially outward. So we have this, okay? Electric field directed radially outward. Now, let us take a small elementary area on the outer region of the Gaussian surface. So as we did earlier, okay? So we have this. So let n cap be the unit normal drawn on the elementary area. And n cap, that is unit normal, gives the direction of vector area. Okay, so we have this. So it gives the direction of vector area. Okay, so we have this. So we have this. Now from Gauss law, okay, so I'm writing from Gauss law, okay, total electric flux equals surface integral of electric field throughout the Gaussian surface or closed surface equals 1/epsilon 0 times the charge inside the Gaussian surface. Now the charge inside Gaussian surface is Q. So we can write in this way, Q by epsilon naught or epsilon 0. So let us take this, okay? And we use the condition of symmetry. So we know, or we have discussed earlier, okay? At each point on the Gaussian surface, the magnitude of electric field is constant, and we can see electric field and area vector are parallel to each other. So we can take electric field out of the integral and calculate electric field outside the insulating sphere. Okay, so we can see we have this. Okay, next is constant, that is electric field. Okay, I am writing electric field is constant on Gaussian surface. Okay, this is the condition of symmetry. Condition for symmetry. Okay, and these two conditions are satisfied. So I'm writing directly. Okay, and E is constant, so we can take it out of the integral. Now this gives me the total area of the Gaussian surface. Okay, This is the total area. So this is 4 pi r square. Okay. So we have this. Therefore, we can write electric field outside the insulating sphere, okay, equals 1 by 4 pi epsilon 0 or epsilon naught q by r square. So this is equation 6. So for spherically symmetric charged body, okay, for spherically symmetric charged body, so what we find, the electric field outside the body is same as if the whole charge is concentrated at its center. So this is to be noted, okay. So we can see from equation 6, for spherically symmetric, okay, charged body, the electric field outside the body is same as if whole charge is distributed at its center. Now we have this. So E equals 1 by 4 pi epsilon 0 q divided by small r square. So this is for small r greater than capital R. Clear? We find this. Now we have this, okay, field inside and field, or let me write in this way, okay, field outside this is capital R, okay. This is a charged sphere, insulating sphere, okay. So we have this. So we have this. Now electric field, okay, this is 1 by 4 pi epsilon 0 q small r divided by capital R power 3, and for this we have E equals 1 by 4 pi epsilon 0 or epsilon naught q divided by small r power 2. Now let us find field at the surface of sphere, that is for small r equals capital R, okay. So if we put or replace small r by capital R, then from these two equation, okay, we get E equals 1 by 4 pi epsilon naught q divided by r square. So we have this. So this